What's up? What's up? What's up? It's your boy, the network. And today's topic is subsection 3.5a, distance vector. This is a subsection under the section 3.5, evaluate routing protocol types. This is an objective in the CCNP route exam code 300-101, version 2.0. Let's take a look at the exam blueprint, see where we came from and where we are headed. Okay, this is the exam blueprint, implementing Cisco IP routing, also known as the CCNP route exam code 300, version 300-101. This is version 2.0. Make sure you're studying for the most up-to-date material. We just wrapped up configuring and verifying default routing. We did 4 sections of that. We finally done with that. Now we're moving on to evaluating routing protocol types. As you can see, we can foreshadow that there are 3 types of routing protocols. We're going today we just doing distance vector. Right? After that, we're going to do the next 2 and move on to describing administrative distance, which is below that. Today, again, we're doing distance vector. So what is distance vector? Distance vector is, okay, so as you can see, there's 3 types of routing protocols, not 3 routing protocols. There's 3 types that we can categorize them in, right? Distance vector is a way that a routing protocol determines which way to go, right? But distance, well, they're all determine which way to go, but distance vector uses distance, but it determines that, it measures it using hops, the amount of hops to figure out which way to go. Now, this may be a good thing and maybe a bad thing. For example, let's say I always use United States to, or actually I always use roads to determine, to figure out, to explain networking, right? Let's say you're going from New York to Seattle. I always use those 2 cities, and I'm glad I grabbed a map this time for y'all. All right, so let's say we in New York City, right, somewhere down here, and we trying to get to Seattle, Washington, which is somewhere in here, right? And we got 3 ways to get there, right? We can go this way, and let's say it takes 10 hops. No, let's say it takes 15 hops to get there going this way, right? And that's like probably the most direct route, right? And then let's say we got another way going through the middle. It takes us only 10 hops, right? Instead of hops, let's say they are toll booths, right? It takes 10 hops or 10 toll booths to go through the middle. And if we go all the way down here, it takes us only 5 hops, right? You would think, okay, it only takes 5 toll booths to go that way. But the problem is you going out of your way, right? You going through the southern states, Florida, Louisiana. We might want to stop in Texas for some of the good food and stuff like that, but it's taking us longer to go down this way. I wish I had some, a marker to go down this way. But if we going down this way, it takes only 5. Looking at the map, you see it only takes 5 toll booths. It sounds theoretically shorter, but it's not, because as you can see, you're going through all the southern states just to come back up north to Seattle, Washington, right? And then it takes only 10 hops to go through the middle, right? Through the Midwestern states, going through Missouri and Nebraska and maybe Chicago or something, going through all of this. That's still longer, right? It sounds theoretically shorter because you only taking 10 hops, but that's right in the middle. And then if you go all the way up here, you look on paper, it's like, damn, it takes 15 toll booths. I'm not going to go that way. That's the problem with routing protocols that uses distance vector, because it looks at the shortest amount of hops. So you would think, okay, it's gonna look and see it only took 5 hops to go through the southern states, but it doesn't know that that's actually longer. And the reason why it does that, it determines which way to go, not just by the amount of hops. Actually, just the amount of hops. It might be slower because the bandwidth going through these southern states might be slower too. That's why I said, I try to use the map to kind of compare it. Let's go ahead and move on to the slides to take a look at the official definition. I hope that it kind of explains it to y'all, using the map and stuff. Again, there's distance vector routing protocols. There's a couple of them that are out there, right? Some are in use today, some are not. There's 3 that can be categorized as distance vector. One of them is kind of a special one. First one is RIP. As you can tell, RIP, it stands for Routing Information Protocol. However, this is kind of a dead protocol too. It's one that's used a lot to teach the theory of routing protocols, because it's easy, it's simple to set up, and a lot of the other protocols are similar to to its to like the syntax and how it's used. There's also, we're gonna be discussing a lot about RIP. However, I'm gonna try not to break it down too much because again, it's not one that's like really in use today. I get conflicted reports about it. Sometimes I've been in a forum where I was like, why are we still learning about RIP if it's really not in use today? I work for a managed services provider. We service more than 400 companies. I have yet, we hop on these networks. I have yet to see RIP on these networks. And trust me, we deal with Fortune 500 companies, and like I said, mostly I see OSPF, EIGRP. I have yet to see RIP. However, it's every time I run into learning material, they're always teaching this. So again, I guess it's used today, but whatever. There's also IGRP, Interior Gateway Routing Protocol. That is a predecessor to actually EIGRP. Now, IGRP is really dead. That is really obsolete, outdated protocol, routing protocol. Again, it's been replaced by EIGRP. Please don't say eGRIP in a interview, in a job interview. EIGRP is a Cisco proprietary type of routing protocol, and that is still used today. It's faster. We're going to talk about the pros and cons of each one of these. Okay, so the meaning of distance vector, right? Distance vector technology. Again, a router uses distance vector router protocol. It knows two things: the distance to the final destination, like we did with the map, right? It knows it could take 10 hops, it could take 5 hops, or it could have taken 15 toll booths, right? But it looks at, okay, well, it only took 5 hops to go this way. Let's go this way. Again, it's not always good. As you can see on the map, it went all the way to the southern states to take, only 5 toll booths just to come back up to Seattle, Washington. That's not very practical. So it uses it knows the distance to the final destination, and then it knows which direction to go to. Again, it's not always good to use distance vector routing protocol because of the fact that it uses hops to determine which way to go. But it does know the vector or direction. So you can think of when you think of distance vector, you think of which way to go and how long it'll take to get there. That's what distance vector means. Direction, vector means direction, which way to go. So the characteristics of a distance vector routing protocol. I know I'm just reading these PowerPoints, y'all. I took this from the Cisco Learning Network. Again, this is my learning journey. I'm reading myself. I'm letting y'all look at myself, talking to myself. So again, I'm reading this, y'all. I know it don't seem like I'm teaching it, but I'm breaking it down to a way that I understand. Characteristics of a distance routing protocol. It uses periodic updates to give routing updates. That's what a routing protocol does. It gives. Okay, we learned a new way, and we learned a new way how to get to Seattle, Washington, and gives updates, or it basically lets other routers know in the path, about this new way to get somewhere. They are periodic, though. In other words, it's a set timer on how often to give these updates. RIP, for example, by default, it sends out updates every 30 seconds, right? It's maybe a good thing, might be a bad thing. Most likely it's not a good thing because it gives the whole routing table and it gives it every 30 seconds. I might not need I might not get an update. It might not be new information, but I'm gonna get an update anyway. That's why, it's slow and it takes up, it uses up bandwidth when it sends out these updates. Characteristics of the distance routing protocol. It knows about the neighbors. Everybody knows about all the neighbors, and it sends the whole routing table. Again, right there it says it. Entire routing table is included with routing update. It might not even be an update, but you're gonna get it might be not no new paths. Might be not no. Did I just use a triple negative? I need to work on my grammar, don't I? There might not be a new routing update or new path or somewhere, but you're still going to get the update. This is not good all the time. You would think, because you're getting updates, it's good, but if there's no new information and you still get the update, you're using bandwidth, you're using processing power on the router. Distance vector routing protocol. Routing protocol algorithm is defined as a procedure for accomplishing a certain task, right? So the algorithm is kind of like a math problem, or a computation that the CPU on a router will use to accomplish these tasks: sending and receiving an update, calculating the best path. That's self-explanatory. Calculating the best path, install routes, right? And so, like, for example, with the map, it calculates the best way to get somewhere by, okay, this way it took 5 hops, this way it took 10 hops, and this way it took 15. I'm using those as a simpler number. And that's what the routing protocol algorithm does: determine which way. Should it go to the northern cities? Should it go through the Midwest? Or should it go through the southern states? With the example we used, it's going to try to go through the southern states because it takes lesser hops to go through there. But again, it might not be the best way. It's just going to take it that way anyway. And lastly, detect and react to topology changes. So even though the updates are periodic, you're not gonna get a new update. It only gets these updates periodically. So let's say it's every 30 seconds. For RIP, you got the update at 0 seconds, right? And then before it gets to 30 seconds, it might be a link that broke down, or it might be a link that went down, and you're not gonna get that update until 30 seconds. So let's say the link broke down at like 12 seconds. You're not gonna get that update. You gotta wait till another 18 seconds before you get that update, right? So that's why it's not always a good thing with distance vector routing protocols. It reacts to topology changes, but it don't react to it until the periodic update. So we will discuss what the other updates and why the other ones, the other routing protocols types are better, and we'll discuss the pros and cons after this anyway. So if you can see right here, we already know what a routing protocol does. It tells you about networks that are not directly connected to you. So if, for example, we got the 16.1.0 network, 16.2.0 network, 16.3.0 network. Router 1 does not know about the 3 network, right? It's over here. And router 2, vice versa, doesn't know about the 1 network, which is over here, because he's not directly connected to him. The routing update lets them know how, about their remote networks. So router 2 is going to let router 1 know about the 3 network. Y'all see that? That's why this is blank right here. He don't know about the 1 network, and he got to wait. If it's RIP, he got to wait 30 seconds to get that update, or when he powers on during the cold start. Okay, the criteria used to determine routing protocols includes, I got this in blue for some reason, time to convergence. Convergence, we're going to talk about what that is. That's basically when everybody got, all the routers have all the routes to get somewhere. That's when a route is considered converged. Scalability is another criteria that we use to compare routing protocols. Scalability meaning, is it good for the future, or is it good for, when our router grows, or when our network grows, is it scalable? Resource usage, so we use to determine which one uses the most processing power, or which one does too much calculations to figure out which way to get somewhere. And implementation and maintenance, how much work does it take? There's some routing protocols that's easy to maintain and implement, and some that are just much more complex. For example, OSPF. There's just so many ways to it could be a good thing, it could be a bad thing, because you can fully customize it to how you want it to work, but it can be disastrous at times because you have it so customized. And if somebody come replace you, they're like, oh God, look at all this we got to do to make changes. Here's the advantages and disadvantages. I'm not going to read all this to y'all. We just going to summarize all this and move on real quick. Again, the advantages is simple to implement and maintain. RIP is always used. Like I said, I have yet to see it used in a live network, believe it or not. And I've been in the field for 5 years, networking more in about almost 2 years. But RIP is a simple tool or simple routing protocol to teach about routing protocols. Once you get to OSPF and EIGRP, which is a lot more complex, you'll realize that it's a lot more complex. But RIP is one to use to teach because it's simple to implement and obviously maintain. It says here, low resource requirements. It doesn't really use a lot of processing power. OSPF is one We're going to get into that once we get into link state routing protocols. Remember, we discussed there's 3 types: link state, path vector, and today what we discuss in distance vector. Distance vector uses low or resource requirements, doesn't use a lot of CPU. The disadvantages, it's slow to converge. Again, it uses periodic updates. You got to what for example, I always use ARP because that's the main example for distance vector. It takes 30 minutes to figure out, or 30 seconds to figure out if there's an update or not. And if it's not an update, you're going to get an update anyway. Or if it's not a new route, you're going to get an update anyway. Limited scalability, slow convergence may limit the size of networks because larger networks require more time to propagate. So if you got a large network that's using RIP, everybody got to get the same routing table every 30 seconds. Yeah, I like how I did that. But, you know, that's just a disadvantage to distance vector routing protocols. Also, it's very susceptible to routing loops. We know what routing loops are, right? Basically, it gets an update or there's a path. It's just going to cause your packet to loop all day. Luckily, there's such thing as time to live, which we'll discuss. And there's also, I did a full video. You can look at my CCNP playlist, section 1.3c. We discussed what time to live is, TTL. That's a mechanism that's used to detect a routing loop, not necessarily detect a routing loop, but to kill off a routing loop. And but the thing is, distance vector routing protocols, they are susceptible to routing loops because of inconsistent routing tables that are not updated due to slow convergence and a changing network. So it might take, again, 30 seconds before you get a new update, but you got a loop going on, and you won't get the other way till another 30 seconds. Network discovery. You will learn about these new networks when the router powers on, and they have RIP or a distance vector routing protocol. I keep saying RIP, and we haven't really mentioned EIGRP, or like I said, IGRP is obsolete and was replaced by EIGRP. The thing with EIGRP is that it's a combination. Well, some sources will say it's a combination of link state and distance vector. Some would just say it's a advanced distance vector protocol type. You pick one, you choose one. They say that the first one is not really accurate. However, you'll notice that it does use kind of path. It uses distance vector to determine which way to go, but it also uses link state because, and what that means is if a link goes down, then it gives you an update. So it uses triggered updates as opposed to periodic updates. So that's why we talk more about RIP because that's more of a 100% type of distance vector route protocol. As you can see, initial network discovery, you turn it on, and RIP is installed on there. You're gonna get these networks that are directly connected first, right? You ain't gonna know about. So as you can see, router 3, for example, he knows about the 3 and the 4 network. So the 3 network and the 4 network because they're directly connected to him. He don't know about the 1 or the 2 network yet. He got to wait till another 30 seconds before the network is converged, before he knows about the networks, before router 3 knows about these 2 other networks that are not connected to him. Notice in his routing table, he only knows about the networks that are connected to him. The 0 means how many hops it takes to get there. It takes no hops because they are directly connected to him. And then right here, initial exchange. If a routing protocol is configured, then routers will exchange routing information. Routing updates received from other routers. It checks updates for new information. If there is new information, metric is updated. New information is stored in the router table. So as you can see right here, we're going back to router 3. He learned about the 2 network from router 2. The 2 network is over here. He learned about this network after the routing table, the network was converged. So again, router 3 has a 3 network and the 10.4 network directly connected to him. So he already knew about these 2 networks when he was powered on, right? Then he learned about the 2 network, right here, from router 2. He learned about it after the network was converged, meaning everybody got the routing tables. He knows he can take 0.001 to get there, and it takes 1 hop, as you can see, right? So 1 hop to get to the 2 network. I used to count directly on the routers. Don't do it that way. When you count, go on the lines. So like it takes, you're gonna start from router 3. So it takes 1 hop or it takes, I'm sorry, from the 3 network, it takes 1 hop to get there, right? If there was another network right here, it would take 2 hops to get there, and so on and so forth. And router convergence, again, we've mentioned that before, is reached when all routing tables in the network contain the same network information. Other routing protocols don't do that. Everybody got, see, look, if you notice, all 3 of these tables all look the same. They just have different ways to get there, but essentially they're the same information. Go ahead and pause this, freeze frame it. Routers continue to exchange information. If no new information is found, then convergence is reached, right? But the thing with routing protocols or distance vector routing protocols, more, again, RIP, it sends out these updates even if there's no new information every 30 seconds. By default, you can change it to every 15 seconds. That'll be worse though, because you send in the updates every 15 seconds. You might get an update quicker, but if there's no information, you giving me information, you telling me, hey, my name is John, every 15 seconds. Like, okay, I got it. Your name is John. And you tell me again, hey, my name is John. Oh, okay, that's cool. That's cool. Hey, my name is John. And you just like, bro, you told me that already. Yeah. Hey, my name is John. And the dude is telling you his name is John, even though his name ain't changed. He didn't go to the government office to change his name. You still know that his name is John. That information might not be relevant. So that's why it's not always good with these routing protocols that uses distance vector, because distance vector uses periodic updates instead of triggered updates, which would be like if John went to the office, like he told me his name is John. Okay, I got that. He won't tell me his name again until he changes his name and he comes back and tells me, hey, my name is Eric. Okay, that's new information to me now because I didn't know that before. Thank you. I hope that makes sense. Okay, so convergence must be reached before a network is considered completely operable. Reason why is because if the network is not converged, and that's the problem right here. As you can see, this is a large network. We've got 4 regions. I'm not going to count. I'm not going to count all these routers to tell you. If all of these are routing RIP, rest in peace to the person that's got to maintain this network, because it's going to take 30 seconds before the network. It may take longer than 30 seconds. You're going to get 30 seconds for periodic updates if it's running RIP, but it's going to take a long time to process all of these, everybody, for the entire network to be converged. That's why, as you can see, the speed of achieving convergence consists of 2 interdependent categories: the speed of broadcasting route information, the speed of calculating routes. So a network like this running an RIP will take a long time to converge because it takes a while to converge for all the networks to have the same exact routing table. And if a link, let's say for example, if a link goes down over here, a router over here might not get it until another 30 seconds. He got to wait 30 seconds before he get that one. Or he got to wait, if they initially power on, he got to wait till the entire network is converged before he could use that route. Okay, it uses periodic updates to maintain a routing table. Let's try to race through these because we're approaching our time limit. These are time intervals in which a router sends out its entire routing table rather. RIP version 1 and version 2. Those are the types of RIP routing protocols. There's also a third type, which I believe is RIP NG, which is RIP next generation, which supports IPv6. We're not discussing it here because we're going to discuss RIP NG, and I believe there's another an exam blueprint. Let's check. Yes, as you can see, we're going to discuss RIP NG in section objective 3.17. That's what round table maintenance does. There's bounded updates for EIGRP. So EIGRP routing updates are partial updates. So whereas RIP is RIP is periodic. That's a typo right there. EIGRP sends triggered update or partial updates. So it only gives you half of the information because they don't have all of it yet. But let's say like here, for example, it learns a new route. He gonna let these other guys know about it, and he gonna let the other guys know about it once he gets it. He ain't gotta wait till 30 seconds before he lets the other guys know. So they are non-periodic. It's really sporadic, but you're gonna get an update as soon as he gets one. You only gotta wait till an interval, if that makes any sense, to get a new information. Routing table, we're gonna continue to discuss the route table maintenance. Triggered updates, conditions in which triggered updates are sent. Interface state changes, so if a link goes down, or if a route becomes unreachable, or if a route is placed, if you get a new route, basically. So if an interface goes down, you're gonna get an update. If a route becomes unreachable, you're gonna get an update. You're gonna get an update when all these three things happen with a triggered update. This is a way to so the thing with RIP, there may be a condition where on a local area network where everybody's sending an exact update all at the same time. As you can see, it's the same thing as like a collision on the LAN. It's going to use up a lot of bandwidth, and it's just it's crashing, as you can see right here. This bad animation here. All these updates are happening at the same time. Solution to that is ARP Jitter, which is a variable you can use. I'm gonna cross this. I should have crossed this out because again, we're not gonna be discussing too much of implementing or how to use ARP because again, this is ARP. This is pretty much an outdated routing protocol. It's just used to teach how routing protocols work because it's simpler to use. Routing loops. This is vector routing protocols, more so RIP, because EIGRP has ways to kind of mitigate this problem. They are very susceptible to routing loops. Routing loops, as we discussed before, it's a condition in which a packet is continuously transmitted. So it might get information. Let's go back to, we could use this routing table to explain it and stuff like that. But let's say we're going to go back to the roads again. Let's say you go to one toll booth, right? And you tell you, you trying to get to Seattle? Go ahead and take this road, right? You take that one road and go to another route and toll booth. And he tells you, okay, take route B. And another one tells you, okay, take route B. And you come back and you find yourself back in your neighborhood. And you came back home. He told me to go this way. That would be the routing loop because you came right back the way you came from. And that could be a problem because it's going to use up bandwidth, and then the packet is just going to be going in the loop, in a circle. And that's what these basically route tables, that's what's going on here. It comes right back. Luckily, there's time to live that would stop this from happening. And we've discussed what that is. That will, kill off a routing loop. But again, RIP and distance vector routing protocols, they are susceptible to it. Our EIGRP has more mechanisms to stop this from happening. Routing loops may be caused by incorrectly configured static routes, incorrectly configured route redistribution. We talked about what route redistribution is in the last video, I believe. In the last couple videos, we talked about what static routes are as well. Slow convergence, because if it takes 30 seconds if I got to wait 30 seconds to get some new information, I might be sending packets to a route that might cause a routing loop. And I'm not going to stop this routing loop from happening until I get new information, which is not going to come to me until another 30 seconds. Routing loops can create the following issues: excessive use of bandwidth, CPU usage, network convergence is degraded, routing updates may be lost or not processed in a timely manner. I know I'm reading this to y'all, but again, I'm reading this to myself. I'm letting y'all listen in. Okay, so routing loops are susceptible, or distance vector routing protocols are susceptible to routing loops. You could it sets a maximum to stop this from happening, right? It takes, I forgot to let y'all know, RIP uses the maximum of 16 hop counts. So if it knows it takes more than 16 hops to get from New York to Washington, New York to Seattle, Washington, then it'll discard it from its routing table. It will consider that network unreachable. As you can see, it sets a specific metric value to indicate infinity. That's what distance vector routing protocols do. So again, the maximum hop count for RIP is 16 hops. If it takes 17 hops to get there, it'll consider it unreachable, if that makes any sense. Preventing loops with hold down timers. Hold down timers allows a router to not accept any changes to a route for a specified amount of time. The point of using hold down timers. So does our EIGRP. I believe OSPF uses hold down timers too. You can call this except they call it dead timers, right? It will consider it dead if it hasn't heard from the other router. The point of using hold down timers allows routing updates to propagate throughout the network with the most current information. So as you can see, this timer right here, it keeps going down. It keeps going down until it gets here, and then it pretty much considers the timer up. The split horizon rule is used to prevent routing loops. A router should not advertise the network through the interface which the update came. We discussed this, I believe, in the frame relay video. If it receives an update through one interface, let's say right here, router 1 only advertises this 10.1 network to router 2, right? And as you can see, router 2 only advertises the 3 network and the 4 network. So the 3 network and the 4 network to router 1. He not going to router 2 is not going to explain or advertise 10.3 network and a 10.4 network to these guys, because they already know it. Because if he advertises it to them, let's say if they don't have split horizon, if he advertises these networks to them and they do the same thing and don't have split horizon installed or configured, they're going to send the update back, and then you're just going to have a routing loop. And that's what split horizon does. It prevents these updates from happening. These two routers giving the same update to each other. That's what split horizon does. Split horizon with poison reverse, a rule that states that once a router learns of an unreachable route through an interface, it advertises it as unreachable back out the same interface. So poison update is basically once it learns, okay, this route is unreachable, he's not gonna let these other guys know about it. Basically, he will just set the hop count to get here to 16, as you can see, and let them know it takes 16 hops to get there. They are just not going to put it in their network. I mean, in their it would just be considered, as you can see right here, it would be considered unreachable. So once he sends this poison update to router 2, right, he's going to set that to 16. Then 10.4 will be considered unreachable because it takes more than 16 hops to get there. Remember, RIP, 16 hops is the maximum hop count. So a poison update just kind of lets everybody know it takes 16 hops to get there. Then they're gonna be like, oh, that's too much. We're not gonna take that way. It's unreachable. I hope that makes sense. We discussed what time to live is. If you don't know, go back to, I believe, 1.3c. Anyways, time to header is a field in the IP header. Lets everybody know. It stops route loops from happening, basically. I'm not going to discuss too much of that. Again, if you want further information on that, go back to the other video. It basically stops loops from happening. Routing protocols today, RIP version 1 and version 2. Again, I said I have yet to see them being used on the live network. As you can see, these are pros and cons to them, right? Slow, small for scalability. Use of VLM, no. A VLSM, no. Yes for router 2, okay, woohoo. And then router usage, okay, it's low here and simple to maintain, but look, it's slow and small for scalability. RIP is not very, there's barely any pros to really use it. That's probably why it's not really in use today. But again, I've received conflicting information every time I research this. EIGRP is slow, small. No for VLSM is low resource and simple to maintain. However, this was replaced by EIGRP, which is these are both Cisco and Cisco proprietary. EIGRP, I believe they became open source, meaning anybody can pretty much use it on any router, and anybody pretty much can kind of modify it. It became a standard about, I think, in 2013, I believe it was. It is fast, large for scalability. Yes, you use VLSM, as you can see. Medium resource usage, however, is complex to maintain and implement. It is simpler than OSPF though, but again, this is used today and it is considered a distance vector routing protocol, but it is distance vector and it uses some link state updates as well. So that's why it's considered, some sources may consider it hybrid, some don't, meaning it uses both. It's categorized as both the distance vector and path vector, distance vector and path vector. As you can see, I put a strike through on these. Routing protocols used today. It's not really used today. I have yet to see it again. If you do know some networks, don't tell me, but let me know if you've seen some in the comments below. Crossing these out, we're not going to discuss too much of that. Features of EIGRP, it uses triggered updates. So if there's a link that goes down, that's when you'll get an update. Hello protocol to establish neighbor adjacencies. So it's just going to keep saying hello, 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 just to determine the network is up or the neighbor is up. It supports VLSM, route summarization, use of topology and to maintain all routes. It's classless, and it's Cisco proprietary. It says Cisco proprietary. This is old because it's now you can use it with any vendor with EIGRP. This information, that's why I said to make sure your information is updated. I got these slides from Cisco Learning Network. This is, that's probably why it says RIP used today, because this is old information. These slides here. So the summary, characteristics of distance vector. It uses periodic updates, right? So RIP, for example, I always use RIP because that's the one that's 100% distance vector. You use 30 seconds. You can modify it to give updates. Routing updates include the entire table, whereas EIGRP, it sends you the entire table, not an entire table, but it sends you partial updates, meaning partial information. It gives you new information. Neighbors are defined as routers that share a link and are configured to use the same protocol. So if they're using two routing protocols, they are not considered a neighbor. However, if you do route redistribution, they will become neighbors. Discovery process through DV, not domestic violence. The distance vector, directly connected routes are placed in the routing table first. So you're going to know about the ones that are directly connected through a cable first, and then you'll get the new information. Convergence is reached when all routers has the same information. Sending periodic updates. EIGRP sends triggered updates, like I said before. We're starting to sound like a broken record. They are prone to routing loops, which is a problem. These are the issues that routing loops that can be caused by a routing loop, or that can cause a routing loop rather. And this is what routing loops can cause. So this can cause routing loops, and this is what a routing loop will cause. Crossed out RIP because it's not really used today. EIGRP has some, like I said before, it uses some features of link state routing protocols and some features of distance vector. That's why it's not considered a 100% distance vector. It says here Cisco proprietary, but you can use it with Juniper, you can use it with Brocade, you can use it with other vendors. And that's pretty much it. We try to race through these slides. Next, we're going to do, I believe, link state routing protocols. For now, please comment, like, subscribe to the network.